Alice and Bob are back playing a stone-taking game, but this time with a twist. On your turn, you can grab all the stones from the first X piles, where X can be anywhere from 1 up to twice a shared counter M, which starts at 1. After a player takes their turn, M is updated to be the larger of its current value and the number of piles they just took, so the limit grows as the game goes on. Both players take turns picking piles this way, with Alice going first until all the piles are gone. Take more piles now, and you can actually lose the game. Alice moves first, and grabbing the biggest pile feels safe, but it hands Bob an even bigger move right after. I'm Kai, welcome to Fun with Learning Technology, where problems most people panic, scroll fast become things that click in minutes. Stick around, by the end you spot this exact trap in seconds. Picture a checkout line. You can only grab items from the front, never reach into the middle. Same here. Piles sit in a row, and every turn you take some number off the front, call it X. You can take between 1 and twice your current limit, and after your move, the limit becomes whichever is bigger, the old limit or how many you just took. Alice goes first and both play perfectly. No heavyweight algorithm here. Recursion and a dictionary is the whole toolkit. What makes it worth learning is where else this shape shows up. Poker boards evaluating hands, auctions ordering bids, chess engines picking moves. Anytime two players alternate over a shrinking resource, this exact pattern solves it. Say our row is 2, 7, 9, 4, 4, 26 stones total. If both players play their absolute best, Alice ends up with exactly 10, Bob gets the rest. There's one small trick that makes finding this fast instead of slow. Which one? Hold that thought. 3 things power the solution. Recursion with memoization means we solve each smaller subgame once and reuse the answer. A dictionary gives instant lookup for a state we've already solved. And suffix sums let us grab the total of every pile from some point onward without re-adding anything. The obvious move feels like take as many piles as you're allowed right now. Take 2 piles first, 2 plus 7, 9 stones, but now Bob's limit doubles and it cleans up the rest for 17. Take just 1 pile instead and Alice ends up with 2 plus 4 plus 4, 10 stones. Taking less right now wins. Here's the trick. It doesn't matter which piles got taken earlier or who took them. All that matters right now is where we are in the row and what our current limit is. I call this the growing window because the limit only ever grows, it never shrinks back down. 2 numbers, index and limit, fully describe the rest of the game and that's what lets us solve each state exactly once and cache it. In short, the whole messy history collapses into just 2 numbers. Remember that trick I mentioned? Here it is, we pre-compute for every starting index the total of every pile from there to the end, the suffix sum. Instead of re-adding piles every time we ask how much is left, we just look the number up. At index 0 here, everything left sums to 26. The recurrence is your best score from here equals everything remaining minus whatever your opponent scores best from the state you leave them in. You try every legal number of piles to take and keep whichever leaves you with the highest score. Full disclosure, the first time I wrote this I forgot to update the opponent's limit too. Not just the index, spent an hour chasing a wrong answer before I caught it. Get that part right and the rest falls into place. First we build the suffix sums by walking backward from the end, so suffix at any index holds the total of everything from there onward. Then an empty dictionary, memo, will cache every state we solve. The DP function is the whole game in miniature. Nothing left, score 0. If twice the limit already covers every remaining pile, just take them all. Otherwise try each legal move and keep the best. Every result gets cached before it returns. Here's the whole thing in one place, same logic you just saw. Fit together, build the suffix sums, define DP with its 2 easy exits, try every move in one line, cache it and kick it off with DP of 0, 1. Clean. That condition checks. Is twice the limit, at least what's left. At index 3 in our example, 2 piles remain, 4 and 4. Twice our limit covers both, so we just take everything. And max of the limit and M is why the limit only ever grows. Take 2 piles, and everyone's stuck with a limit of at least 2 forever after. Watch the actual calls. DP at 0, 1 compares taking 1 pile against taking 2, and taking 1 wins, 10 beats 9. So Alice takes the 2. Bob's best move turns out to be taking 2 piles, 7 and 9, leaving Alice the last 2 piles, 4 and 4. 2 plus 4 plus 4, 10 stones. Exactly what we expected. Quick one for you. Piles are just 2 and 2. Alice moves first. Limit starts at 1. Pause the video and work out what DP at 0, 1 returns here. Drop your guess in the comments. Before you keep watching, I want to see who gets it. For piles 2, 2, Alice takes one pile. Bob is forced to take the last one, so Alice gets 2, not 4. Because taking both right away would need a limit of 2, which she doesn't have yet. Two real mistakes people make: caching by index alone when the limit matters just as much, and resumming remaining piles instead of using suffix sums. Instead of recursion, you can build the same DP table iteratively, starting from the last pile and working backward. It avoids recursion depth worries, which barely matters at 100 piles, but makes the take-all shortcut and loop bounds a bit fiddlier to write correctly. Same complexity either way, honestly just a style choice. There are at most n² distinct states since both index and limit range up to n. Each one tries up to n possible moves, so that's big O of n cubed overall. With n capped at 100, that's about a million operations, nothing to worry about. One pile, twice the limit, trivially covers it. Alice takes everything. Piles that are all the same value, the code doesn't care, it still finds the optimum split. And the base case, nothing left, returns 0, handles the game ending cleanly, no matter how it got there. Stone Game 2 collapses into just two numbers, where you are and your current limit, the growing window. Suffix sums make totals instant instead of re-adding. Remember that greedy trap from the start, taking two piles first actually loses. 9 versus 10 because it hands your opponent a bigger limit. The portable lesson: anytime you see a two-player turn-based game, think relative score between the players, not raw points, and ask whether the state collapses to just a couple of numbers. Want to take this further? Stone Game 3 drops the limit idea entirely. You can take 1, 2 or 3 piles no matter what came before. Worth a look. This algorithm took me years. A like and a follow take 1 second combined. If something feels off or missing, or you want to see something new, tell me. Here's one for you. If M ever gets big enough that Alice could grab every remaining pile in one turn, what does she actually do? Pause it and think. Take a second. Think about what that growing limit really lets her do. She just takes everything that's left. Once 2M covers the rest of the row, there's no strategy left to compute. She banks it all. Round 2. Why can't Alice just greedily grab the two biggest piles each turn? Why does that actually lose? Think about what a greedy grab completely ignores. Greedy ignores that her pick sets Bob's next limit. Grab too much now, and you hand Bob a bigger window. That's the trap the DP avoids.